Today we have a distinguished speaker, Professor Miroslav Krstic, and Professor Miroslav Krstic has served as professor and senior associate vice chancellor for research at UC San Diego, and is the current editor-in-chief of IEEE Transaction and Automatic Control. He is a recipient of the IEEE Brockett Award and Bold Prize, ASME Oldenburg Medal, Siam Reed Prize, Bellman Award, and other recognitions, including the Chestnut and LgV Prize, as well as several IFAC-TC awards. He's a member of the Serbian Academy of Sciences and Arts and fellow of IEEE, IFAC, Siam, ASME, AIAA, AAAS. He has served as fellow ambassador to the French CLFs and as a distinguished visiting fellow of the UK Royal Academy Engineering and Japan's GSPS. Professor Krstic was editor-in-chief of Systems and Control Letters and senior editor in Automatica. He is a co-author of 19 books and several hundred papers on various nonlinear, adaptive, and infinite dimensional control subjects. And welcome to, sorry, welcome us, sorry. Welcome, Professor Krstic, and you can start your talk now.
Thank you very much, Hunting. It's a pleasure to be here. It's impressive what you're doing. It's impressive who you've already had here in this seminar series. I haven't had time to watch the videos yet, but probably will. And good to be here. I've had to make a choice of a topic that aligns with the subject of the seminar series. DDLC seems to stand for data-driven learning and control. So it could have been neural operators for PDEs, but I know that this is a subject that is of somewhat narrower interest to specialists in PDEs. Could have been something about population dynamics in infinite dimension. That's always interesting. Predators, preys, competitive interactions, and so on. But knowing that Andreas in particular, and I'm sure his team as well, work on transportation, traffic, and such things, I picked something that combines learning with vehicles, although in this case it's not groups of vehicles, but control of single vehicles. I also think it's in the era of reinforcement learning, where adaptation is used offline to achieve optimality after the fact, or adaptation may be used online to achieve optimality in the limit as time is already over, that it's good to provide a little bit of exposure to the possibility of achieving optimality actually in real time for unknown systems, thanks to learning. This is a topic that has interested me for nearly 30 years, but I felt it was too complex until I recently came across a problem where it is not, and it is perfectly suited for it, and that's the problem of control of non-holonomic vehicles. I will tell you about something that is called optimal adaptive control in the context, rather than adaptive optimal control or adaptive dynamic programming, but optimal control that is adaptive in the framework of controlled non-holonomic vehicles, parking, and extended subjects for vehicles that are not necessarily ground vehicles. The subject of non-holonomic vehicle stabilization starts with Brockett's condition more than 40 years ago, where he established the well-known conditions that preclude the possibility of stabilization by static feedback. And he first formulated it as an impossibility of stabilization by feedback that is smooth, but this was later generalized to the impossibility of feedback that is even discontinuous by Jean Ryan, Jean-Michel Caron, and Lionel Rosier around the year 1991. So close to a decade after Brockett, it was shown that it's not only the smoothness that is a problem, or even continuity, but using static feedback period without time variation. So people turned their attention in the early 90s to doing something that Brockett doesn't prohibit, and this is using time varying feedback or some hybrid of switching algorithms for parking. That results in motions that, you tell me if you think that this is a desirable way to park a car. Do you do that? Please don't. Please practice better and park the way you're supposed to. So time varying feedback is a mathematical solution, but it's not the answer to what we practically want. And then, given that stabilization by feedback is essentially impossible, attention has turned over the last 35 years to open loop solutions, either completely open loop motion planning or motion planning combined with tracking of those planned motions, planned trajectories, path following, and so on. But anything that at its heart has an open loop trajectory is not robust to disturbances. You might have a car, or you might have been a car that can self-park. That is entirely open loop. Sure, it does the job. It might be impressive that it's done without a human, but it's not an impressive control accomplishment to simply execute an open loop trajectory with a nonholonomic vehicle. What we want, if we can get it, is parking and other vehicle motions that are entirely feedback driven. Motions that are natural, human-like, but executed only in response to the current state. No open loop component, no history. We want parking trajectories that, depending on where you start in the space, and if this is the parking slot with this position and orientation, that you perform motions the way a human would do. When appropriate, move purely forward and park in this spot with this orientation, or when appropriate, back up and park, like, for example, this light green trajectory and so on. How do we achieve this purely by feedback? Is it even possible? So Brockett tells us it's not. And I will develop results that are purely feedback-based, and I will have to reconcile how this kind of parking maneuvers are possible in contradiction with Brockett, Caron, Rosier, and Jean Ryan. Bear with me until we get to that point. I will be developing feedback laws for stabilization, which means that I will be developing control Lyapunov functions. And the moment I develop control Lyapunov functions, the question, if you've been around control Lyapunov functions, the question is, okay, you had this controller to find a Lyapunov function. Now, why this controller in particular? Control Lyapunov functions open a whole big world for you of designing other controllers. And in particular, designing controllers that are of this LgV form, or if you're not familiar with this Lie derivative notation, designing gradient-like controllers for systems for which you have a CLFV. If you can design LgV controllers, you get something for free, and that is optimality in the sense of a meaningful cost of control and on the state. So the moment you stabilize with the Lyapunov function, you have a path to optimality. And once you achieve optimality, you get something that all optimal controllers have. Maybe this was not taught to you in your optimal control class, but it's a fact that optimal controllers have the property that you can increase their gains arbitrarily and they're still stabilizing, or that you can decrease their gains down to 1/2 and they're still stabilizing. They have this incredible gain margin from 1/2 to infinity. So this is a tempting, I would say, irresistible direction once you achieve stability to aim for a lot more. And once you achieve more, namely stabilization that is optimal with known parameters, then you ask yourself, what if the parameters are unknown? I've been around adaptive controllers a lot. Can we produce controllers that are not only adaptive, but that are optimally adaptive? Not in the limit as time goes to infinity, not reinforcement learning type adaptive dynamic programming, but optimal over the infinite horizon from time 0 until the end of time, rather than only at the end of time. I will skip this part on neural operators. I have this removed this from my slides just to finish on time. Finally, once you master the parking maneuvers, somebody asks you, as happened in my case, you can do parking. Well, imagine now that the parking spot is moving. What do you get? You get the problem of pursuit evasion. Forget the ground vehicle. Forget ground vehicles. Imagine that you're in the realm of, let's say, aerospace vehicles, and the parking spot is trying to escape, and what you and it's no longer a parking spot. It's target intercept. Can you extend the parking results to pursuit and evasion results? So I'm going to cover those grounds. To solve these problems, several conventional things need to be abandoned and changed significantly. They relate primarily to the starting point, namely the model. So I will introduce two transformations that make it possible for me to do something that wasn't possible before. First of all, a near sacrilege. This familiar model, the basic, simplest ground vehicle model, the unicycle model that you all know, whose states are the Cartesian position xy and the heading theta, or some of you might know it as the Dubin's vehicle model. I will step away from this model and do something that is not my invention. It was invented about 30 years ago by a group of roboticists in Italy. Make a switch to polar coordinates. The change from Cartesian to polar coordinates is very basic math, and I will not bother you with that. This is trigonometry. I'm changing from x and y into rho and delta. These are the Cartesian coordinates of the position of my vehicle that I'm parking relative to the target position for that vehicle. Rho is the distance, so this is a positive quantity. Delta is the angle in the polar coordinate system. And instead of the heading theta that I had here, which is an absolute heading, I will consider the relative heading, namely the line of sight angle theta. This is common in aerospace guidance and navigation systems. So this will be now my three-state model. There will be two angles the polar angle and the line of sight angle and the distance. On the right-hand side, the inputs are still there. The input v, the longitudinal velocity, and the angular velocity omega. So I still have those inputs, but the drift, I'm sorry, there's no drift. The vector fields have changed. And you see a division by the distance, namely potentially division by 0, and that might make you worry. In fact, the presence of that is what makes everything doable. It's a blessing in disguise that disappears in the polar coordinates. Does this model fail Brockett's condition? It doesn't. It passes Brockett's condition. So I have to reconcile this thing that, I've made a change of coordinates that allow me to pass the Brockett condition, but I can't cheat Brockett's condition in the Cartesian coordinates. Bear with me. This is not something I can explain at the beginning, but only after the result. There is a second change in the model that is crucial if I'm more than parking, if I'm conducting pursuit and evasion. So look at this polar coordinate model one more time. Let's now suppose that I'm taking the longitudinal velocity to be constant. So now I'm just doing parking by steering, and my foot is on the gas pedal without speeding up or slowing down, without braking. And let's consider that model. If you change the time variable from the regular time t into a new time, which is related to the distance, which is ln of the reciprocal of the distance, or the sort of negative of the ln of the distance, you get this model. If you're seeing it for the first time, it's overwhelming. But think of the red simply as a time-like variable. And in that time scale, the right-hand side of the model has two states: delta, the polar angle, and the tangent of the line of sight angle, which goes to infinity as your line of sight turns from pointing towards the target to pointing away from the target. When you point perpendicularly to the target, this tangent gamma blow up. Look at the second order system. This is actually a chain of integrators. This is the time-like derivative of delta equal to the second state, and the time-like derivative of the second state is equal to something where the steering input appears. In other words, this is feedback linearizable. If you treat this distance-related quantity the distance to go, so to speak. If you treat the distance to go to the target as time, the system is feedback linearizable. So you bet I'm going to exploit that. I haven't seen this observed. It occurred to me as I was trying to go from parking to pursuit. Let me now tell you which way I'm going to go. I'm going to get to parking a bit later. Let me start from what seems to be as the more difficult of problems: pursuit of targets. That problem is solvable, at least in a way that is known to me, and I believe that it's a fundamental limitation. That problem is solvable not globally, but only half globally. If you start pointing away from the target, I don't know how a controller for that could be designed. But if you start pointing at least a little bit less than perpendicularly, not away, but at least a bit with the target in sight, those problems are half globally solvable. I will first show you something that is easier, namely the pursuit of a target that is not moving. It's not really a pursuit of a target. It's simply parking in finite time with a constant velocity. And then I will move to a moving target where the target acts as a disturbance, and you have to pursue the theoretical design using input to state stability. So let's say the target is stationary, and you want to get to the target at a desired direction. How do you do that? None of these designs are simple, and I will not be able to explain how exactly one gets to these controllers. I can explain what these controllers guarantee. I think that given that I've shown you the conversion of the model into a feedback linearizable form, the space in between, namely the design of the controller, is possible to fill if you read the paper. But let's see what these controllers achieve. So let's take a controller for a vehicle that has a constant positive velocity, and let's design only the steering feedback for that vehicle. That design is based on backstepping of a particular unconventional kind. And that design is applying angular velocity, namely steering, in response to the distance rho, the line of sight angle gamma, and the polar angle delta. And what is it achieving? It is achieving this pair of results. Let's look at them line by line. First, the distance is governed by this inequality. T1 is a certain finite time that gets longer if the initial distance is larger, and that gets longer if the line of sight angle is larger, and so on, but it's finite. So what does this expression say? It is linearly decreasing in time. In other words, you get to the distance 0 in finite time at least a linear rate. In other words, you manage to park. Now, the question is, do you end up parking at the desired heading, theta equals 0, back in the original coordinates? And do you achieve this parking maneuver with a steering angle that is finite? Because you see this division by rho in here. If rho is going to 0, it seems like, you might, the steering might go crazy. No, quite on the contrary. The steering and the heading angle not only go to 0, but go to 0 infinitely smoothly. This is what this exponential of the negative of 1 over the linear expression does. This yellow rectangle not only goes to 0, but all of its derivatives go to 0 as well. All right. How does this look in terms of trajectories in the Cartesian space? This is that parking maneuver. You wouldn't object parking like this. You wouldn't object going to a target with a desired heading being behind the target with this kind of trajectories. All right, let's now say, okay, you can get to a target that is not moving, but what if the target is both moving with a positive speed, let's say a fixed wing aircraft or some other vehicle, and also maneuvering? It steers, and you don't know it's maneuvering. It acts as a disturbance. How about that problem? So first, what is the model? Well, I've shown you the model of the unicycle in the polar coordinates, and that was the model without these gray terms. But when the target is maneuvering, what happens is that there aren't any extra states. In the relative coordinates, it's still 3 states. But you have these additional gray terms. The target's speed, VE, where E stands for the evader, enters these 3 additional terms. And think of this as basically now a drift vector field because VE is constant. And the target or the evader is steering. This is a disturbance not known to the pursuer. And if you studied nonlinear control and robust nonlinear control and robust backstepping and so on, when you see a disturbance that is not matched by the input, you go, darn, if only it were matched, I would be in a good, easy territory. I could not cancel it, but I could dominate it easy. I try sliding mode control, for example, if I know a bound on the disturbance. But I'm sorry, it's not, because it's a different vehicle. It enters its own equation. So now one has to roll up one's sleeves and use advanced tools of robust nonlinear control, not sliding mode control. So now we have to set some ground rules. If the pursuer is to capture the evader, the pursuer cannot be the slower of the 2 vehicles. The pursuer needs to have a kinematic advantage. The ratio between the speeds needs to be in the pursuer's advantage, at least a little bit. This epsilon must be positive. Now, additionally, if you want to design controllers that are not incredibly complicated to the point where they're not presentable in a seminar, but something that is manageable, you want to give the pursuer the ability to accelerate and slow down in addition to steering. So I will give myself I will allow myself to speed up or slow down the pursuer in accordance with the line of sight angle. If I'm heading almost perpendicularly, I'm going to accelerate the pursuer. The important part is the steering feedback of the pursuer. It's given by these 3 lines. It's again a backstepping-like controller whose input produced is omega p, the steering of the pursuer, where the backstepping transformation is given by this, and where in between I have this expression omega p bar, which enters in here. It's not rocket science, believe me, even though it's not a simple expression. You look at the result. There are transformations. You need to do the algebra, and this is where you end up. It can be made simpler, but then it gets more conservative. This is a non-conservative but complicated design. What does one get at the end? Well, let me go quickly through this. You're familiar with already the notion of capture. The distance goes to 0 linearly and becomes 0 in finite time. It's longer if the initial distance is longer. It's longer if the kinematic advantage is very small. In other words, if I'm barely faster than the evader, it'll take me more time. But capture is inevitable for the evader. And finally, this is the most interesting part. This is where it gets mathematically advanced. The capture at a desired angle. The conventional pursuit evasion is purely geometric. You apply directly the heading input. It's not a state. For 60 years or more, since Rufus Isaacs, the pursuit evasion has been really not dynamical, but geometric. This is now non-holonomic and dynamical. And the goal is not just to get to the target, but to get to the target at the desired angle. I will let you think of reasons why you want to get to the target at a desired angle. You know, I don't want to be explicit, but the reasons are very good. So do you get to the target at a commanded angle, for example, without loss of generality, the angle of 0? The answer is here. Both of the angles are bounded by this expression. This expression is multiplied by a quantity that goes to 0 in finite time. The fact that the target is maneuvering and that this is an unknown function, but bounded, doesn't matter. The target, the evader, stands no chance in spite of maneuvering. This inequality is input to state stability, but stronger. In input to state stability, you would have a class KL function only for the part relating to the initial condition. Here, there is a quantity that goes to 0 that multiplies the input. In other words, this is input to state stability with the asymptotic gain of 0. In conventional ISS, the asymptotic gain is a non-zero function. Here, it's a zero quantity. So capture. Some simulations to show you how this works. The red is the evader. These are 3 different initial conditions just to show you that it doesn't matter where they start. It doesn't matter what the initial heading angles are. The capture directionally, always from behind. This is without loss of generality, the preferred direction of capture succeeds. All right, let me now go back to parking. Now the target is stationary. And the reason why I moved to this second is that the objective is actually harder here. The objective is global rather than half global. And now I'm not dealing with fixed wing aircrafts. I'm not dealing with vehicles that cannot move in reverse. I'm dealing with vehicles that can back up and go forward, just like our actual cars. So in the 3-state polar coordinate model, there are 3 equations, and the first one of them looks like this, if you recall. The design for the forward velocity is nearly obvious. It's this choice. It's a velocity that is proportional to the distance because you want to slow down as you approach the parking spot. And it's also dependent on the cosine of gamma, which in plain terms means that if you're facing more towards the target, you're going to go forward. If you're facing away from the target, you're going to shift in reverse and go backwards. That's the intelligent thing to do. The math leads you to the obviously intelligent choice for the forward velocity. And that's the easy part. The difficult part is the angular velocity. How do you get into the parking spot and you don't end up like this and feel embarrassed and get a ticket, or somebody keys your car because you're such an incompetent driver who takes up 2 spots? All right, so how do you design the steering input? There's a number of ways. And somebody who works on nonlinear control cannot just come up with one way if they know n methods. And n is at least 3 in nonlinear control. The basic forms of nonlinear control are passivity-based, the simplest, forwarding, and backstepping. Backstepping is the most likely to be known to most of you. But let me tell you, I'm going to show you 3 different designs and associated with them 3 different control-Lyapunov functions designed for them. None of them are simple. The control-Lyapunov function for the passivity-based design is not just a sum of squares. Yeah, there's a square of the distance. But then when it comes to the two angles, it's not a square. You cannot accomplish things with a square. You have a sum of squares, and you need a square of that sum of squares. So the simplest passivity-based CLF is already non-quadratic. I have to skip the development of this. This is a whole separate lecture in nonlinear control. How about forwarding? Forwarding is an approach to nonlinear control that is the opposite of backstepping. Backstepping, aggressive; forwarding, cautious. Forwarding minds first and foremost not destabilizing a system that is borderline stable, which is what the unicycle is. So the forwarding-based CLF is a sum of squares, but in transform coordinates. And this coordinate transformation between the polar angle and the line of sight angle is this special function. So it's not trivial. You wouldn't accidentally think of it. Likewise, for backstepping, the sum of squares, but one of the squares is transformed with the arctangent. Backstepping needs to be reined in from being too aggressive by using a bounded change of coordinates such as the arctangent. So what do these steering feedbacks look like? I show them to you just so that it's not left as a mystery. This is what it looks like. Is it obvious? Not at all. This backstepping controller. Not at all. It's not at all obvious why it should look like that. But is it very surprising that there is a whole bunch of trigonometric terms? In fact, almost nothing that is not trigonometric. It's not surprising. It's a system with two rotations, the polar angle and the line of sight angle. And the thing is to get the right trigonometry to enter the steering feedback. And that's what it is. Let me skip that. Let me say very, very briefly. When you have two rotations, your state space for the angles can be the plane, can be Cartesian in the angles. It can be periodic in one of the angles, in which case it's a cylinder. Or it can be periodic in both angles, in which case it's a torus. So lots of interesting things to do in nonlinear and geometric control here, but that's not what the talk is about. Let's get to the bottom line. With the feedbacks designed, and I've shown you both the forward velocity feedback and the steering feedback, what is the end result with these Lyapunov functions? The end result is the classical way of expressing global asymptotic stability using a class KL function. So that's the end result. However, you should now challenge me. All right, you have achieved global asymptotic stability in polar coordinates. Congratulations. But I know Brockett's condition. You seem to be claiming something impossible. So let me now reconcile this. The polar coordinate representation of the unicycle passes Brockett's conditions. This is not impossible. What's impossible is global asymptotic stabilization in the Cartesian coordinates. So what is this expression? What does this bound convert to in the Cartesian coordinates? It converts into this expression. And this expression goes to zero as time goes to infinity, but it does not give you stability because the dependence in the first argument, the initial condition in the Cartesian coordinates, is biased by this expression, which is a non-zero expression. So what do you get? What you get, the proper way to call this, and its conventional name, it had to be invented, is that one gets attractivity and Lagrange stability rather than Lyapunov stability, attractivity and boundedness. Global, uniform, Lagrange asymptotic stability. And here's your acronym for that property. Now, let me tell you one more thing about this, which it's really important to be honest. This, when a system fails to be stable, you have to ask yourself, does it fail to be stable because I can't prove it? Or does it fail to be stable because it's unstable? Well, Brockett says, by the necessary condition, that it cannot be stable. So this result is an achievement of attractivity with instability. So does that unsettle you? In terms of the performance of parking, would you not want to park like this? Either go forward and then in reverse as you've been taught, or maybe go in reverse and go forward if there is plenty of space. Or if you're so far to the side of the parking spot, why reverse at all? You would just go forward, make an S-shaped curve, or you even, if you want to have fun, perform a backing up S shape. That is not unsettling. It's unsettling only mathematically that this happens to be not stable. Because if you shift only, if you get perturbed only a little bit, you're still going to have to perform a maneuver that takes the angle through a transient that is disproportionate to the perturbation, and the perturbation in the angle is zero. That is instability. You can't even see it. You have to be really imaginative to grasp this. This is not instability. This is actually stable, but the price is exorbitant. You would never want to park stably. All right. I will skip a couple results. These results are about parking in finite or prescribed time using time-varying gains or using homogeneous feedback. So it's possible to do that. You've already seen me do it once with constant velocity here. I have two examples of doing it with a velocity that goes to zero. Let me skip those things. They're interesting advances beyond asymptotic convergence, going to finite time or fixed time convergence. Let me now turn the attention to what's aligned with the data-driven learning and control or learning-based control. Let me tell you a little bit about optimality. So the system we're dealing with, the non-holonomic unicycle, is actually a driftless system. There is no drift. There is no f of x. There are two inputs, v and omega, and nothing in addition to that. It's a challenging problem because the state vector is of dimension 3 and the input vector is of dimension 2. It is very challenging. It is very hard to find a control Lyapunov function for such a driftless system. But the moment you find a control Lyapunov function for a driftless system, then any feedback of the gradient form, and this is not just the gradient of v, it's the gradient of v along the direction of the input vector field g, it's LgV, is stabilizing. So these controllers that I've shown you before, including the backstepping control, I can throw it away. And I can now pick even better controllers. I can pick these LgV controllers that use the gradient along the direction of the input vector field g with any gains, small or large. And why is this interesting? Well, first, it's interesting because it happens to be optimal. This is the minimizer of a cost functional that is quadratic in the forward velocity and in steering. And it's positive definite in the three states because LgV can be zero only at zero. So it penalizes the deviation of the state, and it penalizes driving too hard or steering too hard. What do these controllers do? This is what controllers, the basic controllers do, and this is what these optimal controllers do. Please don't jump to the conclusion that one is better than the other. This is just a different option. And you have three gains in the CLFs. So you can shape this tremendously, and you can shape these tremendously. So it's a new catalog of controllers. Let me see how I'm doing with time. What is the steering input doing? The steering input steers and goes to zero. If you're like me, when you look at this as an engineer, you don't like it. Because look at how hard this steering works for some initial conditions. What if I'm limited in steering? Can I do it? And the answer is yes. You can saturate the steering input. You still get optimality, but the optimality is obtained in a particular nonlinear way. You're no longer minimizing v squared omega squared. You're minimizing something that blows up as these inputs exceed their limits. You have optimality in not only can you use saturated feedback. Saturated feedback is optimal with respect to something meaningful. And what do the simulations look like? They look like this. A highly restricted steering, fully utilized. Look at this guy. It falls asleep. It works super hard at the beginning, gets lazy later. This one uses the nearly full control authority all the time because it has little of it. So to me, it's a feedback that's basically indestructible. You apply any gain, it works. You even saturate it, it still works because it always works in the right direction. The trajectories actually hardly change. It's just the speed of travel along these trajectories that gets affected by the input. Finally, let's now add adaptation. So back to this vehicle model, the polar coordinate representation of the unicycle. Let me now include uncertainties. The unknown B1, which makes steering authority unknown to the designer. I'm sorry, which makes the driving authority, V, unknown to the user. And the unknown quantity B2, which makes the steering authority unknown to the user. Both of them are positive. We're not talking about the sign being unknown, but the magnitude being completely unknown. Not only within some range, completely unknown. So what do you do in this situation? And what do you do in particular if you want to simply augment the good designs that you have in the non-adaptive setting, namely the LgV designs? You use these adapted gains, epsilon 1 hat and epsilon 2 hat. How do you adapt them? You adapt them using these adaptive update laws. They're derived using some Lyapunov functions using a Lyapunov-based design. A Lyapunov function that combines the parameter estimation error with the CLF for the vehicle. So look at these designs. This is a bit more general than what would be simply clear. But these are designs that update the gains, that raise the gains at a rate that is proportional to the square of the LGVs. And if you take this function n simply as linear, this numerator becomes constant, and you have simply a normalization by 1 plus the Lyapunov function v. So the simplest form of this is just LGV squared divided by v. A normalized update in proportion to LGV squared. You almost would heuristically think of this, but it works theoretically as well. So what is theoretically provable? First, stability is theoretically established in terms of the Lyapunov function or the measure of the state of the vehicle alone. What is VA? VA is a special Lyapunov function for the overall system that combines the parameter adaptation and the vehicle dynamics. It is not a sum of Lyapunov functions. It is not a simple composite that you would think that's the first thing to try. No, it's not the first thing to try. It's a composite that combines the Lyapunov function with the vehicle together with the exponential of the Lyapunov function for the parameter estimation errors, epsilon tilde and epsilon 2 tilde, which are defined here relative to the estimates epsilon I hat. This happens to be positive definite. If you take 1 plus v1 times the exponential of v2 minus 1, this is actually positive definite in v1 and v2. Well, let me skip this. This establishes that the parameter update stops and doesn't exceed a certain value. But what's most important for the vehicle itself is that it gets parked at the desired position and heading. Now, this happens to be optimal, and this is the gist of my talk's title and the whole talk. This is what's relevant to the contrasting of this methodology with adaptive optimal control, in contrast to what I'm doing, which is optimal adaptive control. So this adaptive control that I showed you is the minimizer of this cost function. What's in the bracket you've already seen, and I hope you agree that this is a meaningful way to penalize the inputs v and omega and the states which are captured in LGV. So positive definite in all the states and quadratically penalized in the inputs. But the adaptation is penalized as well. It is penalized in this function psi of epsilon tilde. Let me remind you what psi of epsilon tilde is. No, sorry, I think I have that. So the parameter estimation is penalized here, and it's penalized not quadratically, but exponentially, much more severely than the state, rho, gamma, and delta, and the inputs v and omega. It's penalized through this exponential. So what does that mean? Well, it means that learning comes before control. It means that you're not trying to control a system that you know poorly. You're trying to first, and it's not sequential, it's all simultaneous, but you're trying to do a better job at learning than controlling with poor knowledge. Feldbaum posed this question in his famous book on dual control. He posed this question. How do we simultaneously, these are not his words, do the exploration and exploitation? And this result is an answer to that. Your exploration, I mean, learning has to come first. And this is all closed form. The feedback is explicit, and the value function is the output function VA with its dependence on the parameter estimation error, on the learning error. Now you may ask yourself, well, if he can do it inverse optimally, can this educate us how to formulate a direct optimal? Because we like direct optimal control. Well, you're welcome to try. You follow the logic of penalizing more aggressively the parameter estimation error. What do you get? You get a Hamilton-Jacobi-Bellman equation, which is not only a PD that is difficult to solve and store. It's a PD that depends on the unknown parameters. So the hopelessness of infinite horizon adaptive and optimal control without the inverseness, but in a direct sense, is I think plain to see here. So what is the moral of this vignette? The moral of the vignette is that the formulations of adaptivity and optimality need to be sequenced and prioritized very asymmetrically. And this message could inform formulations of reinforcement learning and serve as guidance and aspiration to those models. So with that, let me stop here. Thank you for your attention, and I'm happy to try and answer any questions.
Thank you, Professor. We received many questions on YouTube. I'm gonna pass the questions to you now. The first question is, dear Professor, are control constraints considered in the controller? I have seen some studies that apply saturation after the deviation of the controller in CLF. In such cases, do we have any guarantees?
Yes. This is a little hard to see because I don't have those slides in here. I have various examples of the forms of saturating the input. Well, imagine phi to be a saturation function. It can be a saturation function of various forms, arctangent or various other things. So the stabilization is guaranteed. The optimality is given with a constant on control, which is the integral of the inverse function of the saturation. And it's necessarily a function that blows up at the control limits. You have to accept that. I mean, you cannot get bounded control without prohibiting the excursion of the control above the bound. And this is one way to prohibit it. A blow up of the input. And as you constrain the control, this affects the state penalty. So imagine if this is arctangent, the state is penalized in proportion to the arctangent. In other words, it's not really quadratic. It's locally quadratic and globally linear. So this formula is telling you, okay, all right, if you're so stingy, if control is so expensive to you, well, then the state excursion must not be that expensive to you. Okay.
Another question from Andreas is, thank you for the great talk. How the proposed CLFs and associated feedback laws achieve asymptotic stabilization without violating Brockett's necessary condition for smooth stabilization?
Can you read
Yeah.
the first half of the sentence? You mentioned something
Yes.
about ISS.
Yeah. So how the proposed CLF and associated feedback loss achieve asymptotic stabilization without violating Brockett's necessary condition for smooth stabilization.
Okay, so maybe I was too fast, or maybe this question came before I went through this. There is no violation of Brockett's condition because there is actually no achievement of asymptotic stability. This result, this is the positive result that we prove, which is not stability. It's just attractivity and boundedness. But if you think about it from the vantage point of Brockett's condition, which prohibits asymptotic stabilization in these coordinates, you know immediately that what's achieved is that the equilibrium is attractive while unstable. I want to be 100% honest. Attractive but unstable. And you don't see that it's unstable in here. But perform a mental experiment of moving the vehicle a little bit from this position to slightly sideways. Any maneuver that gets you back is going to be a maneuver that either takes the angle, which has been perturbed by zero. The angle has the heading angle has not been perturbed at all, and the distance has been perturbed by infinitesimality. You still need to perform a large excursion of the angle, or maybe a large excursion, depending on which of these four parking maneuvers. This is actually four different feedback laws. It's not one. So depending on which of the four families of the feedback realizations you take, something's going to have to get large in the state, even though the state has been perturbed infinitesimally. That is instability. It's convergence without stability. Is this something that is undesirable? This is the best that is possible given Brockett's condition. Is this something that is weird? No, it's not weird. If you look at the literature on stability, this question was explored as far back as the 1950s in Russian literature. This was posed: can I have stability every time that I have attractivity? There are counterexamples to that. In Vinograd's, in a paper by a certain researcher called Vinograd. There are more recent examples, but Vinograd's example you will find in the textbook by Vidyasagar. So I would say that this Brockett system, which makes it impossible to achieve stabilization, but it allows you to achieve attractivity, is the most physically relevant, non-contrived example of this, attractivity without stability.
Thank you, Professor. Do you have time to answer? We have like a couple more questions. If you are in hurry or something, we can end it now. If you do have questions, we can have.
Yeah, go ahead.
Okay.
I do have time.
Okay. Sure. So there is another question. Thank you, Professor. How do you find the CLF to achieve inverse optimality? Is it possible to modify cost functions to derive control and adaptation loss to achieve online stabilization and learning?
What is the last word? Online stabilization. What was the last word?
Learning.
And
Online
learning.
stabilization.
Online stabilization and learning. So all of this is online stabilization, and the online learning is the very last part. So let me remind you, this is online learning. Online stabilization would have been with constant epsilon hats, and learning online is this. How do we, how do you design these control Lyapunov functions? Well, that's the key question. These do not fall out of the sky. These are hard work. These are hours, if not days, of leveraging everything that we know from the existing design theories for nonlinear systems. Yeah, I don't have all the equations that I would use to show you. Let me just tell you that once you substitute the velocity feedback, once you substitute this feedback into the polar coordinate model, the resulting system where only steering needs to be designed to stabilize the two angles, rho and gamma, is a system that is both in the strict feedback form and the strict feed-forward form, but neither one is conventional. In other words, it's a system to which both backstepping and forwarding apply. It's a thing of beauty that you can use both methods, and in addition, you can use passivity-based control. It's just that none of those applies straight out of any paper. You have to custom develop it, and then you end up with these. If you truly are interested in nonlinear control, from this paper alone, you would learn the equivalent of spending a couple months.
Okay, thank you, Professor. Thank you so much. I think the time is passing, so we may conclude here. And thank you today for giving us a really interesting talk, and we really enjoy it.
Thank you so much, and have a good day. Thank you for having me.
Thank you. Bye-bye.